you for your awesome talk.
Yeah, thank you. Thank you for the time.
Thank you.
Yes. Okay, thank you. Bye.
See you. Okay. So our final speaker in the morning is Professor Yiyi Liao. She is an assistant professor at Zhejiang University. Before that, she was a postdoc in Autonomous Vision Group, a part of University of Tübingen and the MPI for Intelligent Systems, working with Professor Andrew Skager. Her research interest lies in 3D computer vision, including 3D scene understanding, 3D reconstruction, depth estimation, and 3D controllable image synthesis. Her topic today is towards generative photorealistic simulation. Okay, welcome, Professor Yiyi Liao.
Thank you. Can you hear me and see my screen? Okay, great. Yeah, thank you very much for having me, and thank you for your introduction, Li. And I will be presenting our recent work towards generative photorealistic simulation. So, first of all, why are we interested in building a simulator? It is well known that in autonomous driving, testing the cars in the real world is quite expensive and is also not very secure. For example, we need a safety driver sitting in the car, and still the security cannot be guaranteed. So instead, we can train and evaluate the autonomous vehicles in such simulators like Color, such that there is no security problem, safety problem. And we can see that, for example, simulators like Color, there is still a clear domain gap to the real world. This leads to a question: can we learn a photorealistic simulator from the real world? There are actually some works in this direction. For example, NVIDIA has demonstrated their simulator Drive Sim, which shows quite promising performance. It looks quite photorealistic. And they can also rotate the camera at a large viewpoint. Despite that, the technique of this drive sim is not fully disclosed. Has been mentioned that this relies on the neural reconstruction method, in particularly the neural radiance fields. So when we apply neural radiance fields to the KD360 dataset, we can also obtain quite promising performance as shown here. So we can do more in this neural reconstruction. For example, we can integrate semantic and instance labels to be able to also render panoptic labels at the novel viewpoints. And this is the work we did in panoptic nerve. And we also considered novel view appearance and semantic synthesis leaderboard in the KD360 dataset that we have released. And we have already received several submissions, and you are also very welcome to join us. So far, we have considered simulation while reconstruction. So this brings the benefit that there's no risk. And compared to existing simulators like Color, it is more photorealistic. But does this solve the problem already? And in my opinion, it does not fully solve the problem. For example, there's a lack of novel objects, and also there's lack of novel scenes. So for example, let's say if we want to turn the ground into grass, or if we want to remove all the buildings in the scene, that's then not easy to do in the current reconstruction pipeline. So the key idea is that now we can achieve this by 3D generative models to produce the novel objects as well as novel scenes. However, if we want to collect a lot of 3D supervision to train such 3D aware models, then this is quite expensive to do. Instead, what we want to do is we want to learn to generate 3D assets with minimal 3D information. And this will be the focus of my talk today. And I will present our recent progress in the 3D aware image synthesis, including generation of objects, human, as well as finally the urban scene. And the ultimate goal is that we want to use minimal 3D supervision to be able to generate such 3D assets. Now let's start with the object synthesis. So this is an early work we did in 2020 named Graph. The idea is that we want to build a 3D aware GAN by lifting the generation to the 3D space. Basically, this is done by replacing the normal 2D generator as a conditional radiance fields in the normal GAN. And in combined with the differentiable volume rendering, we're able to render a 2D image. This is then fed into the discriminator and receives adversarial loss for training. This training pipeline allows us to learn from unstructured 2D images. And we do assume that the camera pose distribution is given because we need to sample a camera pose to render an image during training. But you may wonder, why does it work? Why are we able to learn such complete 3D cars from the unstructured 2D images? Actually, we can think of that using the adversarial loss allows us to fuse multiple information across those 2D images, despite that they are from different instances. And let's keep this in mind, and we will revisit this point when we talk about human synthesis and scene synthesis. So for the generation of the objects, we then further investigated how can we scale this up to higher resolution. As in the original graph, as well as other 3D aware methods like PyGAN, we used the conditional radiance fields to generate an image, which is parameterized as a large MLP. And we can render an image using differential rendering, which guarantees the 3D consistency by design. However, this parameterization with the large MLP leads to quite slow rendering, which leads to very slow training as well as slow inference. That's why it is very hard to scale this up to high resolution. So another line of works instead proposes to render the features at a low resolution and then use a strong neural renderer, which is parameterized as a 2D CNN to upsample this to a high resolution. This improves the efficiency. However, this neural renderer does not guarantee multi-view consistency, as it's simply a 2D convolutional neural network for upsampling. So in Voxgraph, we proposed to improve the efficiency while maintaining the 3D consistency. And the idea is also quite simple and straightforward. It is inspired by the recent progress in accelerating the training, more particularly the methods Planoxel and DVGO, where they use a voxel grid to represent the scene instead of the large MLP. So here we also use the voxel grid to represent the scene. And then instead of using an MLP to generate the scene, with this voxel grid is then generated with the 3D convolutional neural network. And then with the generated voxel grid, we are able to efficiently render an image while volume rendering. And another detail is that we further decompose the foreground and the background, where the background is simply generated by a 2D convolutional neural network, and we compose them while alpha composition. During training, we use pruning and progressive growing. So more specifically, we prune the occluded and low-density voxels for high rendering efficiency. And we use this progressive growing strategy where we start with dense voxel grids at the lowest resolution, and then we gradually improve the resolution of both the voxel grids as well as the image. And then we maintain only a sparse voxel grids at the higher resolution. So now let's look at some comparisons to the existing methods. So we first show a comparison to Stalinov, which uses this powerful neural renderer for upsampling. As we can see that it leads to inconsistency at some regions, for example, at the eyes or at the corner of the mouth. And in contrast, GRAM does not rely on such a volume renderer, such that its performance is also quite consistent, but it leads to visible artifacts by using manifold representation. And in contrast, Voxgraph does not rely on such manifold representation nor neural renderer, such that it leads to multi-view consistent results without artifacts. Here we show some additional results. Here we fix the latent code and rotate the camera. And here we show the interpolation in the latent space. As we decomposed the foreground and the background, so we can also show background removal. And here we show the sparse voxel grids that we learned. We can see that the model actually learns good geometry from the unstructured 2D images. We also have results on cats. And of course, for autonomous driving things, we have results for on cars that are more interesting to autonomous driving. And that's the part I want to share about the object synthesis. And now let's move on to human synthesis. As pedestrians are also very important for autonomous driving things. And here I show a very toy illustration where we insert generated humans to an urban image. This is only a very toy example, but illustrates the idea that we can actually make the autonomous driving simulator much more challenging by inserting generated objects. So yeah, this is a very toy example where we haven't considered the lighting effects, for example, but it illustrates the idea. And the key challenge for generating such articulated humans is that now we actually need to fuse multiple information not only across different instances, but also across different human poses, as each captured 2D image comes with a different human articulation. And here we also want to learn from 2D images. And we then here we assume that the camera pose as well as the human pose distribution is known. Assuming that the human pose distribution is known can simplify the task. So let's compare the human synthesis and the object synthesis. The key difference is that now we have additional degree of freedom, that is the human articulation. And then a straightforward idea is that if we can generate the radiance field independent to this human articulation, then this will simplify the task. So following this idea, there are already some works in this direction. For example, one live work use blend weights to map a point in the observation space to a global coordinate space. And then the radiance field is generated in this global coordinate canonical space. This allows for disentangling the radiance generation from the pose. And this also allows for fusing multiple information across different viewpoints as well as across different articulations. However, learning such blend weights is very hard when there are only unstructured 2D images. And also, if this is learned, then it's actually very hard to generalize to unseen poses. So another line of works instead proposed to a deterministic canonical word coordinate formulation that they use a deterministic surface-based mapping to map the point from the observation space to the canonical space. This leads to then better generalization, but it can also generate ghosting artifacts in the case where, for example, one point in the free space is mapped to occupied space in this canonical space. So we were thinking, is it really necessary to map a point to the canonical pose to be able to fuse the multiple information across different human poses? And actually, this is not necessary. So what we proposed is that instead of using a single canonical word coordinate, we map a point to multiple local coordinates. And this is also done via the deterministic mapping, giving a sampled human pose. With this formulation, we are also able to disentangle the radiance generation from the pose, as these local coordinates are also fixed, predefined, and shared across all the instances. And we are able to achieve better generalization and omit the ghosting artifacts. Here we show a comparison to the surface-based mapping method, where given the input pose, the surface-based mapping method may lead to such ghosting artifacts between the legs, and our methods does not have this issue. Now let me give you a bit more detail about the method. So actually, in our method is inspired by point nerve, where we model the generative radiance fields as based on the vertex. So it's generative vertex-based radiance fields, and we name it very 3D. The vertexes are actually extracted from the simple, so they are the simple vertices. And then each sample point is mapped to the local coordinates of its k-nearest neighbor vertices. For each vertex, we learn the feature using a 2D generator such that they are all shared, and this is efficiently generated. And in combined with vertex feature and the local coordinates, we then map this to the RGB and density. This then finally leads to the rendering of the full image, and we train this with adversarial training, just as the previous method for object synthesis. And another advantage of our pipeline is that we can actually obtain part level control for free. So it means that now that we have vertex features generated by the 2D CNN, and as we can know the semantic meaning of each vertex, we can actually apply PCA to each part individually to allow individually manipulating each part. This is the part manipulation results, where we can manipulate the head, the upper body, as well as the lower body individually. Now let me show you some more results. Here we show viewpoint control of the generated human. And we can also control the shape. This can be achieved by simply manipulating the vertices using the simple parameters. Here we show appearance control by interpolating between the latent code. And we further show part control, where we can manipulate each part individually, including the head, the upper body, as well as the lower body. Here we show comparison to the baseline. Note that this enough method is based on this learned blending weight that I mentioned before, and it leads to much more like artifacts when it is applied to unseen poses. And in contrast, our method generates better to unseen poses. We also have image synthesis results on another dataset, ICLR23. And here we also show viewpoint control, shape control, as well as appearance control. And finally, we also show pose control. Okay, so that was about object synthesis and human synthesis. Now we have these 3D generative models that can generate such 3D assets for objects and humans, and we can finally scale this up to generate urban scenes. And before we dive into the task, let's ask, why is scene generation challenging? Let's record for object generation and human generation. Actually, a very common idea is that we define a canonical space, or actually the model automatically learns a canonical space. This allows for sharing information across the 2D images. So here is an illustration of this canonical space where, for example, actually all the generators will generate the car with the same orientation. This actually allows the car to easily fuse information across 2D images. And this, I personally think, is very important for fusing information across different views. However, for scenes, it is very hard to define such a canonical space for stuff regions, for example, for the background, like road and wall. In that case, then it is very hard to learn a good geometry for the background regions, purely from unstructured 2D images. So there are actually already some works in compositional scene generation, like giraffe and disco scene. So when they model the generative model, they consider the compositional modeling, where they disentangle the foreground and the background. And they use for the foreground objects like cars, they're generated in a canonical space based on the given distribution of the 3D bounding boxes. This is identical of assuming that the camera pose is known in the object generation. However, they consider only static background, which means we are not able to freely move the camera in the scene. And there is also lack of control over the background regions. For example, it's not easy to edit the background regions. So in Urban Giraffe, our goal is to build a generative model that is compositional and controllable for both foreground and background. With that, we are able to move the camera forward in an urban scene, as well as editing the objects and stuff. For example, like changing the building to tree. And the key idea is that we introduce a panoptic prior for coarse geometry and semantic guidance, especially for the background regions. Because this, as we discussed before, learning the background geometry purely from the 2D images is super challenging. And this panoptic prior in the form of semantic voxel grid gives us a good coarse geometry prior. And in this task, we also focus on learning from 2D images, but we do assume that we have coarse 3D information available that is given in the form of such 3D panoptic distribution. Now let me give you some more details about the method. So firstly, we sample from the dataset panoptic prior, which is given in the form of a semantic volume V and object layouts O. So V is parameterized as a semantic voxel grid, and O is parameterized as a set of object bounding boxes. Such semantic prior can be obtained from coarse 3D bounding primitives. For example, this can be available converted from the KD360 annotations, or it can also be inferred from existing semantic scene prediction methods. And one important note is that actually this semantic voxel grid does not need to be very accurate. It's actually quite coarse when we convert this from the KD360 dataset. And given this such semantic prior, we then build a semantic voxel conditioned stuff generator for generating the stuff regions, as well as we have an object generator that is built similar to Giraffe, that's where we generate objects in the canonical space. And additionally, we have a sky generator to generate the sky as well as far regions that cannot be covered by the semantic voxel grid and the objects. And we use a neural renderer for efficiency. And also importantly, this neural renderer allows us to color the objects based on the context of the stuff regions. For training, we use adversarial loss for the full image as well as for the object patches. This allows us to learn better geometry and appearance for the objects. And additionally, we apply a reconstruction loss for the stuff regions, where we show that in the paper we show that this also leads to better fidelity. Now let me show you the more results where we are able to move the camera forward in by training on the KD360 dataset. We can also fly through the scene while camera pose interpolation. So we are also able to edit the stuff based on by editing the semantic voxel grid. Here we change the building to tree one by one. And we can also lower the building. And this comes my favorite one where we can turn all the road to grass. We're also able to edit the objects in the scene, like adding or deleting objects. And editing its appearance. We're also able to rotate the car or translate them. And additionally, we built a toy dataset, Clever W, where we add some words as stuff regions. And we show that our method is also applicable to such things, where we can also edit the objects the stuff and the camera. Finally, we show some comparison to the baseline, where, for example, the giraffe in the middle does not give faithful result when we move the camera forward. And in contrast, our method can faithfully move the camera forward. And now let me give you a short, brief summary. So I believe that 3D-aware generative models, they are very promising for autonomous driving simulation. And by using adversarial training, it actually allows for us to fuse information from different instances and even from different articulations. And lastly, learning from 2D images is challenging, but we can use easy to obtain 3D information such as human pose distribution or like such coarse 3D priors. And of course, those are still very preliminary results for really scaling this up to autonomous driving simulator. And there's still a long way to go. For example, we need to consider better integration, like how we can insert the generated objects or humans to existing scenes. Or we need to also need to consider generating better geometry. For example, the geometry that we generated from urban giraffe is still not that good. And more, we also need to consider more modality, for example, LiDAR and fisheye. And then lastly, we also need to consider more diversity, like generation across datasets, or like some generating out of distribution things, just as mentioned in the previous talk, which is quite important for autonomous driving. So finally, I'd like to thank all my collaborators, and thank you for your attention.
Okay, thank you, Professor Yiyi Liao. Do you have any live questions? Okay, so maybe I have one question. So current like synthesis processes or algorithms, they only like deal with background things and cars. What do you think about like adding people into the or actors into the scene? Yeah, it is not quite explored right now. So what's the challenge? What do you think of that problem?
Yeah, I think, yeah, that's a very good question. Like as I have actually shown already in this very toy example, like if we simply, I think this this challenge comes from maybe two aspects. For example, like in the normal driving things, like normal driving data sets, like Kitty or cityscapes, the human there are actually only captured at a very low resolution. So it is very hard to learn a generative model from those data sets. But then if we learn generative models, for example, then from like fashion data sets or like other human, they're specifically designed for human, and then this may not really fit to the autonomous driving things. So, and also like if we simply integrate like generative things into existing environments, then maybe we also need to consider the lighting effects, and this also should be addressed. So yeah, I think then in general, I think that's very interesting direction, but there's so many challenges that still need to be addressed.
Okay, cool. Thank you. Okay, do you guys have any questions? Okay, thank you, Professor Yiyi Liao. Yeah, so this is our morning session. Thank you all guys coming here, and we will come back in, I think it's 1:30 p.m. Yeah, we will have Jamie Shelton from Wave UK and some other talks from Christos and Professor Bor Lee and